Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means with AP Statistics. This video is going to tackle topic 7.4, setting up a test for a population mean. So to conduct a test for a population mean, it is a 4-step process. This video is going to cover steps 1 and 2, and then the next video for topic 7.5 will cover steps 3 and 4 and go through the entire problem. All right, so what exactly is a test for a population mean? Well, we've already talked about confidence intervals. So at confidence intervals, we don't know the population mean. So we use a sample mean and sample standard deviation to estimate it. Well, in a test, a statement is made about the population mean. However, someone, maybe a fictional person in a problem, believes the population mean to be either higher, lower, or simply different. Our job is to use a sample as evidence to help see if the belief is true or not. So a confidence interval, we're just looking for the population mean. We don't know what it is. We want to find it. In a test, somebody makes a statement about what that population mean is. And we think, or a fictional person in a problem thinks, that it's something else, higher, lower, or different. And what we want to do is prove that our claim that it's higher, lower, or different is correct. So here's an example. The makers of a popular caffeine pill want to make sure that their tablets don't contain too little caffeine. So they inspect a random sample of 35 tablets from a production batch and measure the caffeine in each of those pills. When the production is working properly, there's a mean, mu, this is a population mean of all the tablets, of 220 milligrams of caffeine. So the statement's been made that the true mean is 220 milligrams. We're concerned that maybe the pills are having too little caffeine, and we want to test this claim and see if it's correct. All right, so how do we answer this question? Well, if we're going to answer this question, the first thing we need is the mean and the standard deviation from our sample. So remember, they looked at a sample of 35 pills, and the mean and the standard deviation of that sample was 218 milligrams, and the standard deviation is 3.2. So now we have to slow down for 1 second. And this is a big step in the process. We have to ask ourselves, are we seeing a mean of 35 tablets? Yeah, it's a little bit less than 220 milligrams, but the question is it just a little bit less because, hey, you know what? Samples vary. It's a little bit less. Guess what? Another sample could be a little bit more. It might not mean anything. Or is 218 milligrams significantly less to a point that we should be like, whoa, let's stop production. Our pills obviously have less than they should. And that's the whole point of a test, right? So if we're going to answer this question, if we're going to try to prove that we're right, that the amount of caffeine in the pills is too little, then we obviously have to start with these two numbers, the mean and the standard deviation of our sample. All right, so here's the kind of the 4 steps that I mentioned. These 4 steps should sound familiar because they were the same as when we worked with proportions. First, we need our null and alternative hypotheses based on the problem. Then we need to build a sampling distribution on the null being true. We have to believe that the null hypothesis is true. And that would be that there is 220 milligrams of caffeine in the pills, because that's what's supposed to be true. So we just have to believe that to be true. Now that sampling distribution is going to have to follow a t-distribution. Remember why, right? The big issue that we have is that we're only using the mean and the standard deviation of our sample. And when we only use the mean and the standard deviation of our sample, that's where we're not as confident to use the normal model. It's not going to be as accurate. So we're going to have to use this t-distribution that we've already talked about as well. All right, now the sampling distribution will also show us what all possible sample means we'll look at. And that is really what's important, because then we could say, where does our 218 fit in? Okay, and that's actually step 3, is locating our sample mean on that sampling distribution. We're going to have to use a t-score because it's a t-model, and we're going to talk about that. And we're going to have to calculate the p-value for our data. And then with that p-value, we can make a decision. All right. So let's work through all the steps. Again, this is a 4-step process. This is called a 1-sample t-test for a population mean. So it's a t-test because we're using a t-distribution. Please, this might actually come up on the AP test. Why are we using a t-distribution? Because we only know S, the sample standard deviation. We do not know the standard deviation of the entire population, unfortunately. Sorry. So that is why the t-model is needed. All right, so let's talk about step 1. Step 1's actually pretty easy. The first is naming it and giving the hypotheses. So it's actually a couple different things here. We have to identify the parameter of interest, right? You want to make sure that in your name, you're talking about what it is your problem's focusing on. And we're focusing on the mean amount of caffeine in milligrams in our caffeine pills. It's going to be a one sample t-test for population mean, and then we have to give the null and the alternative hypotheses. Now, I'll be honest, these first two things that we could actually do all at once, because we could just say, hey, we're going to conduct a one sample t-test for the population mean amount of caffeine in all of the caffeine tablets. So we could kind of name the test and give that context of what the question's about all in one sentence. And then we do have to name the null and the alternative hypotheses. Let's review that really quickly. So every one sample t-test starts off with a pair of hypotheses, right? Kind of like in science class. You have the null hypothesis and the alternative hypotheses. So the null hypothesis is the situation that is assumed correct unless evidence suggests otherwise. So we use a little h sub 0. So the null hypothesis is what we read, what the problem says is true. For us, that's 220 milligrams. And the alternative hypothesis is what we think, right? This is our thought. What we're hoping evidence supports. This is what we're wondering. We're wondering, is it really less? And that is h sub a, the alternative hypothesis. Now let's talk about a one-sided test versus a two-sided test. So a one-sided test is when your alternative explores the thought that the population mean is either greater or less than the original assumed population mean. So anytime your alternative is using a less than sign or greater than sign, we call that a one-sided test. We either care about the top or the bottom. So if we think about that t distribution, that is very symmetric, looks a lot like the normal distribution, but it's not. If we think about that we only care about our alternatives that we think the truth is greater, then we only care about this top tail. We only care about being significant on that top tail. So again, in any problem, you got to read it, right? You determine the level of significance. So if you're going to use a level of significance of 1%, then we're talking about that top 1% that is going to tell us that, wow, this is significantly high. Or if our alternative is less than, then we're only going to look at that bottom tail. And once again, if our, let's just switch it up. If we're going to use a 5% significance level, then we're saying anything on that bottom 5% is what we would be deemed significant, okay? Now, a two-sided test is when the alternative is simply exploring the idea that the truth is something other than what you heard was true. This is when you're going to use a not equal to sign. If your alternative is a not equal to sign, you just care that it's something else. Well, then this is where we actually call this a two-tailed test. Because if I'm on this bottom tail or this top tail, then that would be significant. So if my alpha level is, say, 1%, then I'm actually looking at the top 0.5% or the bottom 0.5% to represent my 1% that I'm deeming significant. Okay, and we've talked about that before, so hopefully that makes sense. The only real issue that you have to remember is if you have a two-sided test, because you're using a not equal to sign, when you get to the very end of the problem, all you really have to do is double your p-value before you make your conclusion. All right, so let's make this easy, right? Step one for our example should be very simple. This will be a one sample t-test for the population mean amount of caffeine in all tablets produced by this company. And like I said, I tackled a lot in just this sentence. So I did the name, I named it, say one sample t-test, and then I gave it all that good thick context there, right? You want to make sure that you are giving the context for what the problem's about. Don't just be generic, okay? All right, so my null is that true mean, right? I'm using mu here. Don't ever use x bar. X bar is just a lonely old sample. I'm saying that true mean is 220 because that's what the problem said. That said that the tablet's supposed to have an average of 220 milligrams. So that's my null. And then my alternative is my thought, what I'm wondering. And we were concerned that maybe the tablets have too little caffeine in them. So that's our alternative. And this is going to be a one-sided test because we only care about being on that bottom side. So a couple things you're going to always notice here. Anytime you're working with means, you're always using mu. Those two symbols are always going to be the same. Don't ever put an X bar there. Don't accidentally put a P there. That was proportions. That was unit 6. So always use a mu. We're talking about a population mean, right? It's in the name. It's a population mean. So don't forget that's mu. And then the other thing is that these numbers are always going to be the same. You're never going to have two different numbers there. So you have a null of what you heard was true, and then you either think it's less than, greater than, or maybe not equal to. In fact, that's the only thing that does change between the null and the alternative is the symbol in between them. All right, so step 2 is now building and checking the conditions for our sampling distribution, okay? So once the test is named and the hypotheses are established, it's time to move on, right? So here we actually have to create a sampling distribution on the assumption that the null hypothesis is true. So we have to find the mean, the standard deviation, and the shape of the sampling distribution, all on the assumption that we know the population mean mu from the null hypothesis. Oh yeah, and don't forget to check the conditions too, so we will review those. So again, remember what a sampling distribution is. It doesn't show a population, it doesn't show a single sample, it shows the mean of all possible samples. So sampling distributions are actually filled to the brim with sample means, tons and tons of sample means, and I want to know what is the mean of all those samples, what's the standard deviation of all those samples, and of course, what is the shape of all those samples. All right, so once again, why does it all start with sampling distributions? This really is the most important factor in all of this. We must assume that the null hypothesis to be true and build a sampling distribution based on that value of mu. So yeah, we might think that the true mean is less. Whoops, sorry about that. But we have to assume that the mean that we heard was true is smack dab in the middle, okay? Remember, sampling distributions show all possible sample means. And this is the most crucial part to us understanding what's really going on. Because once we can make a picture of all possible sample means, then we can see where our sample fits in. And that's going to tell us if we have a significant sample or a not significant sample. All right, so let's go over the 3 parts to our sampling distribution. Okay. First, we have the mean. This is literally a mean of means. So it's a perfect symbol. It's a mean of all sample means. And we're going to use the null for that. Now, that little 0 there just means it's the null. Doesn't mean it's 0. I'm just saying it's the null. It's the mean from the null. Remember, we use h sub 0 to represent the null hypothesis. So mu sub 0 is just me signifying that that is the mean from the null hypothesis. Okay? Now, of course, that's only going to be true if the samples are selected randomly to avoid bias. Now, this is why we're actually going to end up using a t model instead of a normal model, is because we have to use standard error here. We're going to replace sigma with s, the standard deviation from our sample. This is going to call us, or have to cause us to use standard error, and that's why we're going to have to using a t model. Don't worry about that too much because we've already talked about that, and we're going to talk about it more in this video as well. It's actually pretty easy. Now, the only way that this form is going to work is if our sample size is under 10% of the population, so independence is assumed between all of these millions of samples that are represented in our sampling distribution. All right, and then finally, what's the shape? Now, again, I don't want to use the word normal here because it's not, but the shape is the t-distribution. But remember, the t-distribution, well, it's not one of them, right? There's tons of them, so it's all based on your degrees of freedom. So it's your sample size minus 1 is how many degrees of freedom you have. That will tell you what t-distribution to use. But the good news is, remember, the t-distribution looks an awful lot like the normal distribution, so it's really not a huge issue, or it's not anything that we, any brand new thing we have to explore here. Now, the condition to use a t-distribution is actually one of 3 things. Doesn't matter which one, you can meet any one of these. A, if it already says that the data for the population follows a normal model, well then my goodness, any sample size is big enough. You can even use a sample size of 2 and you're big enough so that your sampling distribution will be safe to use a t-distribution. Now a lot of people might say, well wait a minute, well if the population is normal, why do we still have to use a t-distribution? Remember, a t-distribution is needed because of this. Because we're replacing sigma, the standard deviation of the population, which we don't know, with S, the standard deviation of our sample. That's why the t-distribution is needed. So even if you know that the population of all caffeine in all pills is normal, doesn't matter. You're still going to have to use a t-distribution because you don't know that sigma value. Now, the other thing that could happen, this is kind of the best case scenario, if you ask me, is that your sample's 30 or larger. If your sample's 30 or larger, then central limit theorem says, hey, any t-distribution is safe as long as your sample is 30 or larger. You don't even care what the population looks like. All right, and another issue is this. If the sample is less than 30, and you never heard or read that the population is normal, then what do you do? Well, this is where you actually have to look at your data. You have to check your data, the data you have. You have to look at your one sample and make sure that it's no major outliers, no major skewness. You basically want to make sure that your sample looks, dare I say, normal-ish, right? It's not going to be perfect, especially if it's small, but you just want to make sure that there's no major outliers, no major skewness. Because remember what we learned way back in 7.1 is that samples reflect their populations. So if your sample looks no major skewness, no major outliers, then you're probably okay to proceed forward. Okay, so a lot going on there. So as long as all of those conditions are checked, as long as you found the mean, the standard error, and the shape, then you're ready to proceed. So let's take a look what that looks at for our caffeine example here. All right, so the first thing I want to do is run through the three conditions real quick. So the sample of 35 tablets was random to avoid bias. That needs to be checked off. The sample of 35 is assumed less than 10% of all tablets. I mean, you got to assume if it's a big company, they make hundreds of thousands of caffeine tablets. So 35 is under 35 or under 10% of them to assume independence. And since 35 is larger than 30, it's going to be safe to use a t-distribution. And again, 34 degrees of freedom. Because remember, there's tons of different t-distributions out there. Now, the mean is, again, assuming the null is true, the mean of all possible samples should be 220. Because that's what the company says should be true. So that's exactly what I'm going to go put right smack dab in the center. And then the standard error, again, this is why I have to use a t-distribution. I can't say that enough, is I'm going to take the standard deviation of my sample. Let me just write this information real quick here. If you remember, the mean of our sample was 218. Sorry for my messy handwriting. And the standard deviation of our sample was 3.2. So I'm taking that 3.2, I'm dividing it by the square root of my sample size, 35, and that's how I get the standard error at 0.541. So I actually drew a picture of this, right? And this is a t-distribution. I know it looks a lot like the normal distribution, but hey, that's kind of what it is. It's just, I mean, in theory, it's a little bit flatter, just a little bit, and a little bit more spread out. But in theory, it's a lot like the normal distribution. All right, so here's my t-distribution. Notice my center is the null, what I'm assuming to be true, 220. And then I went up 1, 2, 3 standard deviations, down 1, down 2, down 3 standard deviations. I take that back, standard errors, right? Because I can't use standard deviation. Now, I don't want to, give too much look into next topic, even though you probably see where we're going with this. The next step is going to be saying, okay, remember my sample of 218? Where does it fall in this? Is it significantly low or just a little bit low? And, I don't want to say it out loud, but you could obviously look at that picture and answer that question right away. We'll talk about that in the next video, though. Remember, this video is just about getting everything set up with step 1 and step 2. So let's do a quick review of step 1 and step 2, because this is actually pretty simple. I want this to be easy for you. So step 1, identify the parameter of interest and name the test. It's a one sample t-test for a population mean. And then you could continue that in one sentence. Hey, this is a one sample t-test for the population mean, and then give the context after that. And then you need the null and the alternative hypotheses. Step 2, got to check those pesky conditions and then build the sampling distribution, right? Find the mean, find the standard error, and find the shape of your sampling distribution. You technically do not have to draw a picture, but I'm going to always draw a picture because to me a picture is worth 1,000 words, and sometimes seeing the picture helps you visualize what's going on a lot nicer here. All right, so what I want to do with the time I have left in this video is I want to explore a very special type of problem. And the reason why we're exploring this is because to solve this type of problem, you do need what's called a one sample t-test for a population mean. But it's a special type of problem that we actually started talking about, honestly, a long time ago back with experiments. And this is called a matched pair t-test. And this is a very special case. It doesn't happen too often, but it does come up. So a matched pair t-test. Let's talk a lot about this. Now, later in this unit, right? Not now, later in this unit, we are going to explore a two sample t-test that looks at the difference between two population means. So maybe I got a mean of Americans versus a mean of Canadians, or a mean of boys versus a mean of girls, or a mean of tigers versus a mean of lions, right? Two different population means, and I'm going to look at the difference between them. I'm not doing that right now. But in this special example, initially it does look like you have two samples, but you really don't. And that's kind of the hard thing with this, is that you need to identify that it's going to look like there's two samples, but there's really not two samples because there's only one sample that you just looked at twice. And that's where it comes a matched pair. Now, you might not remember this. It's been a while since we learned about a matched pairs experiment, but let's kind of just do a quick recap. So, once again, it's going to look like you have two sets of data, but they really only came from one sample. Okay, this is data that is coming from a matched pairs experiment. And that is why you need to recognize a matched pairs experiment to see that this is happening. So if you recall, in a matched pairs experiment, you have one sample of people or objects and you measure them twice. A couple of examples are like if you have a group of people, you measure them before and then you measure them after. So maybe you measure them before they take a pill and then you measure them after they take a pill. So you only have one sample of people, but you have two measurements from them. And what matters most is not what happened before or what happened after. It's the difference between that one person's before and after. Another example could be you do something with your left arm and you do something with your right arm. So again, it's one person that does something with each arm. Maybe I put suntan lotion on one arm and I put a placebo on the other arm. But again, I need to be blinded, so I don't know what's on which arm. And I want to see the difference between the severity of the sunburn on each arm. So at the end of the day, it's going to look like I have two sets of data, left arm and right arm, but I really don't. I just have one sample that I looked at twice. Another example could be you give treatment A and you give treatment B. Like maybe a matched pair design is you have a plot of grass and half the grass gets fertilizer A and the other half gets fertilizer B, and you want to look at the mean growth between the two plots of land. But what you're actually looking at is the difference between fertilizer A and fertilizer B, right? Because this is a matched pair. You had one plot of land, everything was kept the same soil, same weather, same water, same grass type. The only difference was half got treatment A, half got treatment B. So that would be an example of a matched pair design. Now, in all of these cases, the idea is it's going to look like you have two sets of data, but you really only have one set of data, and the set of data you care about is the differences. So you got to emphasize this, and I got to make sure I spend, some quality time on this, because later on in this unit, when we get to a couple topics later from now, we are going to start looking at two samples. But that is when you clearly have two samples, boys, girls, Americans, Canadians, right? We're not talking about that right now. We're talking about one sample that gets measured twice, okay? So the hardest part of a matched pair t-test is just first recognizing that the two sets of data really come from one sample. So you gotta really make sure that you read this carefully. In this special case, you treat the problem as a one sample t-test, but the one sample you care about is the differences between the values in each pair. So you don't care about the before, you don't care about the after, you don't care about the left and the right arm, you don't care about treatment A, you don't care about treatment B, you care about the differences between every single subject. So the null hypothesis is that there is no difference. There is no difference. There is no mean difference. And the alternative is that, no, I think there is a positive difference greater than 0, a negative difference less than 0, or just that there is a difference. So do not treat this as a two-sample test. Now, we haven't even learned a two-sample test yet, but eventually you're going to learn it. And when we come back to a problem like this, or maybe you see a problem like this on the AP test, you got to recognize that it's not a two-sample test. It's a very special type of test called a matched pairs t-test, okay? I think that that's pretty simple and straightforward, but again, it's going to take some time. The best way to get through this is honestly, look at an example. So here's a great example of a matched pair example. So an experiment was performed to see if there's a significant difference between two different brands of thermometers, A or B, used to take the temperature of patients at a hospital. So 11 volunteers are used. Each randomly had their temperature taken first with thermometer A or B. So like, Judy came up and we said, all right, Judy, we're going to randomly determine which thermometer to use first for Judy. We're going to give her that thermometer, take her temperature, wait 10 minutes, and then take the temperature with the other thermometer. And then when David comes in, we're going to do the same thing, randomly determine which one he gets first. So at the end of the day, every subject got their temperature taken with thermometer A and thermometer B. And the question is there a difference that the two thermometers are significantly, or is there evidence, that the two thermometers are significantly different from one another? So here's what this is going to look like, right? You got all this great data in front of you. Temperature A, temperature with B, you got your subjects. There's my 11 subjects. So for example, volunteer 1 had a 98.2 temp and then a 98.4 temp. Now again, it looks like I got 2 samples. But if you read the problem, you realize, no, I only got 1 sample. I measured twice. That's a sign of a matched pairs test. All right, so at the end of the day here, all I care about, I do not care about thermometer A. I do not care about thermometer B. I only care about the differences. What I'm looking to do is find a mean difference. That's what I need. What is the mean difference? So for example, for subject 1, the difference was negative 0.2. For subject 2, and I'm trying to do all this in my head, the difference was positive 0.5. So I'm doing A minus B. So one thing you could do is on your own, you could go and find all those differences. You'll even notice subject 5 had a difference of 0. So it would not take that much work to, on your own, go and find a list of differences. Create a list of differences. And that is all you care about. You do not care about A or B. You only care about those differences. Now, I have seen on the AP test, when they give you a problem like this, they try to help you out, and they'll actually make all the differences for you just to kind of save you a little bit of time. Now, another thing I'm going to show you right now is how you could use your calculator to save that time for you. So if you go to your calculator, and if you need to pause the video to do this, go ahead. But in list 1, type in the temperatures with A. In list 2, type the temperatures with B. All right, so now I got them all in there. And if you want to pause and take your time to enter them all in there, go ahead. Double, triple check A and B. Then you can have the calculator do all of the differences for you. So check this out. This is really cool. In the home screen, you're going to hit second number 1. So you're literally going to take list 1 minus list 2. And boom, it did all the differences for you. You can actually see them. There's the first one that we already found on our own, negative 0.2, and the second one that was positive 0.5. Then what you could do is, while this is all on your screen, you could hit store, which is right above on, and you could store this as list 3. So what you're doing is you're taking all those differences and putting them into list 3. Then when you go to stat, go back to edit, boom, look at list 3. There's all the differences. So options. You could find the differences on your own. 2, you could use the calculator to find the differences for you like I just did. Or 3, on the AP test, sometimes they'll just give you the differences to save everybody a little bit of time. But remember, all I care about is the 1 set of differences, which is why this is really a 1 sample t-test. So what I need to do is now go to stat, slide over to calc, and I need to use list 3. I want to look at the mean, and I'm going to need the standard deviation of list 3, the differences. So here I go. The mean difference is 0.0545. So very, very small difference between these temperatures readings, and a standard deviation of 0.333 if you round that correctly. So the mean was 0.0545, and the standard deviation was 0.333. Sorry, my O's are terrible looking there. 0.0545. So now you're going to run a 1 sample t-test looking at the differences, okay? All right, let's check out the 2 steps for this. So step 1, hey, this is a 1 sample t-test for the mean difference between the 2 brands of thermometers. I'm looking at the mean difference. I don't have 2 different populations. I don't have boys versus girls. I don't have Americans versus Canadians. I have 1 set of differences, and I'm looking at the mean of those differences. So the null is that, excuse me, nah, no difference. So notice what I did here is I actually added a little DIFF for difference. So I'm just emphasizing this is the mean difference. So the null is that the true mean difference between temperatures taken with A and temperatures taken with B is 0. There is no difference between these 2 thermometers. And the alternative is, well, go back to the problem if you need to. I just want to say, is there a difference? And that's why I'm using a not equal to signs. This is a 2-sided test. I never said, hey, thermometer A is less or thermometer B is more or anything like that. I just simply said, hey, is there a difference? So once again, notice I am using mu here. I have to reference the true difference. And the null is that it's 0 because that's the null. I'm going to assume that there is no difference. And now I want to prove the alternative is that there really is a difference. All right, so step 2 here is going through my conditions. So the sample of 11 differences came from people who were volunteers, which I didn't mention earlier, but that did kind of sound shady. But remember, which thermometer that they got used first was random, so that is why I could still avoid bias. Okay, the sample, excuse me again, sorry. The sample of 11 differences is assumed less than 10% of all differences between readings. I mean, there's millions of people out there that could have used the two thermometers. So I'm thinking 11 subjects that gave me 11 differences is going to be under 10% of all possible readings between these two thermometers. And now the sample of 11 differences is under 30. Uh-oh. So I do have to take a quick look at the data and make sure that there's no major outliers or skewness. This is important because this does happen quite often. Now here's the good news. The data is already in my calculator. So in my calculator under list 3 is the set of differences. What I want to do real quick is just take a quick look at a graph of it and watch how easy this is. We talked about this already in a previous topic. Second, y equals, go to your stat plots, turn plot 1 on, highlight the little histogram, and then make sure you choose list 3. That's where I put my differences. All right, and then once you're done with that, just do a zoom 9er, and there's my data. Now, it obviously doesn't look very normal, but no one ever said it had to look normal. We just want to make sure there's no major outliers. I don't see any major outliers, and no major skewness. I mean, it doesn't look great, but guys, remember, there's only 11 values, so it's not going to look good at all. But I don't see any major skewness at all. I mean, listen, it doesn't look pretty, but it's the word major. I don't see any major outliers, no major skewness. So you know what? A t-distribution with only 10 degrees of freedom is totally okay. So remember, the mean is based on the null. The null is that there is no difference. So I'm going to go ahead and assume that the mean of all possible differences is 0. And I do have to use standard error, which is once again why this is a t-distribution. So I'm taking S, the standard deviation of my sample, 0.33, and at 3, and I'm dividing it by the square root of 11. I actually got a pretty nice number rounded, 0.100. So smack dab in the middle goes the mean, 0. I went up 1, 2, 3 standard errors, down 1, 2, 3 standard errors. And then now moving forward in the next video, we'll talk about looking for my sample. Now remember, my sample mean was 0.0545. So we have to ask ourselves, where does that fall into the mix here? And you could probably already answer that question, but we'll talk about that in the next video. So at the end of the day, guys, hopefully steps 1, steps 2 are pretty easy, but I did want to spend a little bit of time on this matched pairs test because it is the exact same process as a 2-sample test. But excuse me, it's not a 2-sample test. It's the exact same as a 1-sample test, but it tends to look like a 2-sample test. So I know you're probably bored that I'm already talking about this as much as I am, but it's really important that you understand this because these types of questions do pop up on the AP test. All right, guys, that's it.